What is Newton's first law of motion? Now, Newton, okay, which again is the pioneer in studying forces and how they relate to motions and everything else, discovered this one strange rule. It discovered that an object doesn't change direction unless, or doesn't change location or speed or direction unless you push it or pull it, unless someone disturbed it. Well, okay, fine. So you look at a table, you look at your table, you have your cell phone on there, you have your calculator on there. So you look at it, it doesn't change its place, right? So for example, if you go, before you go to school today, if you left your phone in your room on the table, you will expect that when you go back, that phone is exactly the same location that you left it, right? Because in your mind, an object doesn't just go away on its own. An object should stay where they are unless someone else picked it up for you, right? And that is part of Newton's first law. He said, an object at rest will stay, okay? So yes, I'm talking about the second half of the sentence first, but that's okay. So an object at rest will stay at rest. That means an object that's not moving doesn't just move on its own. If it does, it will be a very scary thing. So an object at rest stays at rest, right? Stays at rest. Okay, now, an object in motion. Okay, now the first part is actually a little bit stranger. Newton also argues that an object in motion stays in motion. Will stay in motion, I guess we don't. Yeah, an object in motion will stay in motion. Now, this is hard to actually wrap your head around though. Now, what does that mean? An object in motion will stay in motion. Now, Newton is arguing that when something is moving, for example, you have an object moving forward. So let's say an object in motion, right? It's moving to the east with a speed of 10 meters per second to the east. Now, Newton argues that even after 1 billion years, this object is still moving to the east with a speed of 10 meters per second. Newton is making this argument. It's no matter how long you wait, that object should still be moving in the same direction, even after millions and billions of years. Now, you might look at this and say, wait a second, no, object doesn't just keep moving and never stop and change direction. No, they don't do that, right? Well, okay, so there's two parts you have to think about. Number one is, okay, was Newton wrong? And secondly, you have to think about, well, okay, where is this supposed to be happening according to Newton's theory though? Now, Newton is saying that an object in motion will stay in motion unless, so there's a third part of this, unless acted upon, so unless the object is acted upon by an external, okay, so external net force. So this is Newton's first law in its entirety. So when I say you need to memorize Newton's first law, I mean you need to memorize this sentence, basically. Okay, an object in motion will stay in motion, and an object at rest will stay at rest unless it is affected by an external net force. You can change the grammar a little bit, you can change some of the wording, but you have to mention have that. Now, what Newton is talking about is that if there's no other forces, right? If there's no external forces affecting it, then an object in motion should stay in motion. Now, and that is something that's weird. I agree. But if you think about it, what if this situation, now you think this situation is impossible because an object doesn't, travel for like 1,000 years. But what if I tell you we're in space right now? Would that make it easier to accept this? In space, when you, for example, throw an apple to the east at 10 meters per second, why would it stop? There's nothing blocking it. There's no air friction, right? Space is empty. If you're not running into a planet, then yeah, after like 5,000 years, a million years, it should still be going east. In space, this is true though. Any object that you lost in space is going to continue going in the same direction the moment that you left your hand, and it's going to continue in that direction forever and ever and ever. It does work like that in space. Now, but remember though, Newton was a person from 300 years ago. They don't even have car in his age, let alone airplane and spaceship. He has never been to space. No one has ever been to space in his time. No one has even thought about space yet, I think, in his time. People don't actually understand what space were until much later. Like the fact that Earth is floating in this empty space, that concept wasn't even that clear yet at his time. So his theory actually works in space, which is amazing. Now, but on Earth, we have a lot of external forces acting on the object, and that's why the object will slow down. So for example, when you push a car, the car will eventually slow down to a stop because we have external forces affecting it called friction. Friction makes things slow down, right? Okay, so now this law is also referred to as the law of inertia. Inertia is how difficult. Inertia is related to your mass, right? So the more massive you are, the more inertia you have. So inertia is how difficult it is to change an object's motion. So how difficult it is to change an object's motion. Now, the more massive you are, the more difficult it is to change your motion. Okay, so this Newton's first law is also known as the law of inertia. Now, I mean, this actually helps you explain a couple of phenomena. For example, now I know this is on the bottom of the page, but we can actually draw it. So if you go to this bottom of the page, right? Look, let's say you're on a skateboard, riding a skateboard or unicycle, whatever. You notice that if your skateboard hit a curb or a piece of rock, you will fly forward. So when you hit anything that arbitrarily, that abruptly stop your motion, then you fly forward. And why? Now we can use Newton's first law to explain that. Here is your skateboard, and here is you, right? And your skateboards and you are both traveling forward. Your skateboard with you on it are both going forward, right? So that means you are in motion. You are in motion. So you have a speed. The skateboard has the same speed because you're together with the skateboard. And then, so let's say, unfortunately, you hit a giant piece of rock, which is stationary. Now, what happened to your skateboard? Well, when your skateboard hit that piece of rock, it's going to stop very suddenly, right? It's going to be stopped by the skateboard. So your skateboard is now not moving. But what about you? So now we think about Newton's first law. An object in motion would like to stay in motion. So you were moving to the right-hand side before. So even though the platform that you're standing on stopped, you would continue moving to the right-hand side because an object in motion would like to stay in motion. So you would like to stay in motion. And that's why you fall off your skateboard and you fly forward. I'm sure you have actually run into this kind of accidents before. Maybe not on a skateboard, maybe on your bicycle. Your bicycle is stopped by the curb and your body just fell forward. Why? Because your body was going forward before. And Newton's first law tells us if an object was going forward before and suddenly something stopped the rest of the system, you will continue stay in motion and throw it forward. Now that's the reason why we have seatbelt, right? Because think about that. Your car is going at 40, 50 km per hour, and then it hit a wall, or it hits a car in front of you, or it hits a tree. What is the speed of your body before the accident? 40 km per hour. What is the speed of your body after the accident? 40 km per hour. Which way are you going? The windshield. If you don't have the seatbelt, the car gets stopped, you won't be stopped. You will keep going at the last speed that you were going. 40 km per hour, then you hit the windshield. Most likely go through the windshield and then hit the wall. So the reason why seatbelt was invented is to reduce the amount of damage that you receive when you hit the wall. So the seatbelt kind of like slow down your descent, right? Slow down your deceleration so that you don't hit the windshield or the steering wheel that you're holding. Because of Newton's first law, your body will want to stay in motion. So if the rest of the car gets stopped, you were in motion, you would like to stay in motion. Now, another one that you can talk about is, okay, right here. An object at rest will stay at rest, right? An object at rest will stay at rest. Now, that is another thing that you can actually explain. Let me use this example. Because a lot of you are learning how to drive right now. Now, when you go into your car, what is the first thing that you do? You adjust the mirrors, right? To your right height. And what's the second thing that you do? You put on your seatbelt, right? And then you key to the ignition, you know. But there is one thing that a lot of people, even sometimes your teacher will forget to teach you, your driving teacher I'm talking about. Adjust your headrest. Now, what is the headrest? The headrest is the, little, cushion on the seat that is supposed to be extended. Now, your headrest, now how does your headrest look like when you sit on your car? So like here's your seat, right? So let's assume that this is your seat and your head is, so you're here, you're sitting right here. So your headrest is this like little cushion. So you should always have your headrest positioned so that it's right behind your head like this. Okay, so that's your headrest, right? You should always extend it so that your head is actually on the headrest. Now, most people don't. Most people forget to do that. Okay, most people forget. Now, what will happen is most people forget to extend it all the way up. So the headrest is kind of like just on the back area or like even lower, which is really bad. Now, here is a very fatal accident that will happen to people if they don't have the headrest set up correctly. Okay, now there is a kind of accident called a rear end collision. Now, what is a rear end collision? A rear end collision is when your car has stopped already, and then some car hit you in the back. Okay, so this is you, and you are not moving, and then there is a very fast moving vehicle behind you, and accidentally they run into you. Okay, so that's called rear end collision. That means you're in front, they're behind, they hit you by accident. Okay, rear end collision. Now, in a rear end collision, you actually get a very specific type of injury called a whiplash. A whiplash, okay, is a injury that's severe enough that it will sometimes kill, whoever that is injured by that. Now, how does that work? Okay, so here we go. So let's go back and look at you in your car, right? So this is your seat, right? This is your seat, right? You're in your car. So this is your, okay, I cannot draw a seat. No, that's not what it looks like. This is your seat, okay? And then we are going to draw you, right? You, the driver, okay? So you're the driver right here. So one day you're driving, driving, you're very happy, you're driving, look at your smile, right? Nice smile, driving. Now, so your car has stopped, right? At this moment, your car has stopped. No one has any speed. The speed is zero, right? The speed is zero. Okay, and suddenly a car behind you run into you. So now, okay, so now you get hit by the car. So everything was at rest. So everything was at rest, right? Everything is at rest. The chair is at rest. Your body is at rest. Okay, how about your head? Is your head at rest? Yep, your head is also at rest, right? So everything is at rest because you stopped your car, right? Okay, so now the car behind you hit you really hard. Okay, the car behind you hit you really hard. So when the car behind you hit you really hard, your car, what will happen to your car? Your car will move forward, right? Because of the collisions. Your car will move forward. Now, the chair is part of your car, yes? The chair is part of your car. So your chair will move forward a little bit. Okay, so your chair will move forward all of a sudden. So your chair now moves forward because it's part of the car and it's bolt down at the bottom, so it will move forward. Now, your body is strapped onto the chair and your back is actually against the, the back of the chair. So your body get pushed forward too, right? Your back, your lower area, they all get pushed forward. Why? Because the chair is pushing you. So there is a chair behind you. It will push you forward too. So suddenly your body moves forward. Okay? But according to Newton's first law, your head was at rest, right? So it would like to remain at rest. Your head was at rest. Without any external force pushing it forward, it would like to remain at rest. So what happens when your head remains at rest, but your body gets pushed forward? Your head is still here. Look at how dead that person is, right? Because your head would like to remain at rest. Now, why doesn't it go forward just like the rest of the body? Why is my head doing this? Because no force is forcing it to go. Remember, you need a force to push the object to go forward. If you have your headrest will push you head forward, but you forgot to extend your headrest. So your head went like, I'm staying. But the rest of your body said, no, we're going forward. Whiplash. Right, that injury, I mean, the worst case scenario is your spinal cord is completely slapped. I mean, your brain controls the rest of your body by, there's like nerves in your inside your spinal cord, and your spinal cord is protected by your spine. But when your head flips backward like this, that spine can be completely crushed, and then the bone is going to go into the nerves, and you'll be paralyzed for the rest of your life. It has happened before. And worst case scenario, you die right there, right? You die right there, worst case scenario. So next time when you go into your car, right? Your teacher's car, your driving instructor's car, right? Make sure that your headrest, after you fix your seatbelt, of course, that's important too, right? Without your seatbelt, you just go forward. When your car hits something, you go forward, and you go through the windshield and you die, right? So make sure, other than, in addition to checking your seatbelt, checking your side mirror, right? Those are good safety features to do. Also, remember to raise your headset, to raise your headrest, right? So that it's the same height as your head. Not like on your leg area, like the head. Like it has to be high enough so that it's actually touching your head, okay? I know it's not as comfortable as having it as a cushion on your leg. I know that's more comfortable. I know that. But hey, this type of accident doesn't happen all the time, but it only takes one time to kill, right? It doesn't happen all the time. You might never run into it. I wish none of you will ever run into the situation. But this situation is not your fault. The car behind you hit you. You don't control that, right? I mean, I was in an accident like this about, I think 10 years ago. I was near my house. I stopped my car and the taxi behind me ran into me. Like, there's nothing I could do. Like, all I felt was, and then my entire body, boom. And then my entire body just went forward. Luckily, I have my headrest on, so my entire body just go forward and nothing happened. My seatbelt stopped me. So I was fine, right? Okay, so Newton's first law, when you actually think about it, explains a lot, right? A lot of phenomenon. Okay, so let's very quickly go through this. So, for example, when you are moving, so let's imagine that you are racing around a track on a go-kart. List 3 times that you actually notice your inertia. Your inertia is kind of like your body. Like when do you notice your own body mass? Now, usually when you're sitting here, you don't notice your body mass. But for example, when your car suddenly stops, right? When your car suddenly stops, you feel like your body is moving forward, even though the car has stopped already. How many of you have had chance to go on is it called a bumper car in a theme park? Bumper car, right? So you're in a car and it's electrically control, and then the rest of your friends on different car, and then you can slam into other people, right? So what happens when you slam into other people? The rest of your body just go forward, right? You can feel your inertia when you're stopping. You can also feel your inertia when you're starting the vehicle. For example, when you're in your car, when you start your vehicle, you feel like you're being pushed to the back of the car. You do have that feeling, right? So you feel your inertia when you're starting your car too. Now, another location or situation that you feel your own body moving either forward or backward is when you're turning, right? When you're turning, you feel like your body is swinging to the other way. Okay, so now you can remember Newton's first law that way. Or there's another way of thinking about it, which is Newton's first law can also be something like this. If there is no net force on an object, that means no external people affecting it, then an object will stay at constant velocity. That means if the velocity was 10 before, it will continue to be 10 in the same direction. If it was 0 before, it will be still 0 in the same direction, which is 0. Okay, so now, last thing, right? So you see, this is the last part. Okay, imagine that the book is sitting on a table. There's a force of gravity pulling down on the book. Okay, so table and book. We know that there's a force of gravity going down because force of gravity always point you to the middle or center of the earth, which always goes down. Now, but this picture is not balanced yet. I can say in this picture, I cannot say that there are no net force on it. Now, what is net force? Net force is total force. So what will be a situation when you have no net force? Okay, now, again, net force. So let me use the space, you know what? The space up here. Let me very quickly mention what net force is. So the question, we already see this word twice, net force. What is net force? Net force is when you sum all the forces on an object together. So sum of forces, sum of all forces on an object is called the net force. It's the total. It's the total force on an object. Now, forces are vector, so they do have direction. So for example, very easy one. So let's say I have Kyle helping me push a box this way, force 1. And let's say Kyle can do it at 200 Newton. And then I'll have Miko helping me pushing it the other way. So Miko push it this way, and Miko has a force right here, F2, and it is 80 Newton. So what is the net force in this picture? Well, the net force in this picture, in this scenario, the net force is, well, 200 Newton is to the right-hand side, 80 Newton is to the left-hand side. So the winner is the 200 Newton in this case. So we'll just take 200 minus 80, which is going to be 120 Newton. So the net force, which is the total force, after you subtract by things that are fighting each other, is 120 Newton to the right-hand side. So net force is just the sum of all forces. Sometimes the right-hand side wins, sometimes the left-hand side wins, sometimes, upside or downside wins. But we want none of these. We want net force of 0. So how can we have a net force of 0? So let's say we have the same scenario, but this time force 1 is pushing upward with 200 Newton, and force 2 is pushing downward with 80 Newton. And now I know force 2 cannot win on its own. So I am going to call a friend. I'm going to say, hey, Manish, help. We are not strong enough. Help. So Manish come in, and he's going to help us. He's going to have a force number 3, and it's going to be exactly 120 Newton. So now this game is balanced, right? The forces go up, 200 Newton. 2 forces go down, add up to 200 Newton. So overall, the net force on this object is now 0 because all the forces balance out. So what can we say? Now this object will obey Newton's first law. Newton's first law is only true if the net force is 0, if all the forces balance out. Newton's law is only true when this happens. Okay, so no force on the object, unbalanced. Now, here's a problem though. If you go back and look at the book on the table situation, the book, force of gravity is a force that goes down. But if the book stays on the table, which it does, right? So if you look at your textbook right now or your page right now, it stays on the table. That means the object at rest is staying at rest. That means the net force must be 0. Otherwise, there's no way the book can stay on the table. Remember, if there's any extra force either on the right or on the left, the object will just go that way. So for example, in this situation, the object will, well, in this situation right here, the object will go to the right? Because the force on the right is stronger. But the object in this situation is going to stay at rest because the net force is 0. Or maybe if it was running at constant speed, it will stay at constant speed because the net force is 0. Now, we look at the book, okay, on the table. I mean, obviously, the book is at rest. But how can we explain the book at rest if there's only one force on it, gravity? We need something to counter gravity. So let's say gravity, let's make up a number. Let's say this is 20 Newton. I need something else that's 20 Newton on the other side. Otherwise, the book would not be at rest. Now, the fact that the book is at rest means there must be something on the other side. So that something has a special name. That something is called a supporting force from the table pushing up, and that force is called normal force. Normal force. So normal force, such a long word to write. Usually we can do a shorthand, Fn, normal force. This normal force will be exactly 20 Newton. That way, gravity and this normal force will balance out, and you have no net force, which means the object stays at rest, right? So in this case, you will have a net force of 0. So you have a net force of 0 because the two forces balance out. Now, first of all, two questions. Number one, why is it called normal force? And number two, what on earth is that? Normal in science doesn't mean regular. Normal in science means 90 degrees. Yes, I'm not kidding. Normal in science actually means 90 degrees. So it's the same word as perpendicular. So normal force means perpendicular force. Okay, if this is a perpendicular force, then we have to ask perpendicular to what? To the table. This supporting force is perpendicular to the surface, to the table that you're sitting on. Okay, so normal force always perpendicular to the surface. So you must be sitting on a surface to receive the support force. So, and that surface could be a table or it could be the ground, but it has to be a surface. Then you can draw a normal force, supporting force pointing upward. Okay. But ladies and gentlemen, what is normal force? I thought we only have 4 types of forces: gravity, electromagnetic force, nuclear strong and weak force. What is normal force? It's not in one of those 4. Now, to answer that question, I'm going to tell you, you have to go through a thought experiment or a thought exercise with me. Okay? And you have to use your imagination. Okay? Now, let's join me in this adventure. Okay? So what we're trying to do right now is I'm trying to explain to you what is normal force. Okay? What is normal force? Now, okay, let's go here. You don't have to copy this down. Just listen. It's a life story. Listen, right? It's a good one. I promise you. All right. So, number 1, everything is made of, right? Everything is made of, you don't have to copy this down. Just listen. This story is nice. Everything is made of matter, right? Okay. So you and me and the table. Everything is made of matter. Okay. And what are matters? Right? You have an atom, right? Matter, which is an atom. Now, so I would like to ask you, what is an atom? Okay, so what is an atom? So an atom is something that looks like this, right? An atom is something that looks like this. So an atom has a nucleus, and inside the nucleus, you have some protons and neutrons, right, floating around. And then this is the nucleus. Now, but what else is in an atom? Come on. Electrons. And where's the electrons? Are they in the nucleus? No, they are not. They are like kind of like floating around like this. And some bigger atom might have multiple layers of electron orbiting, right? Agree? Boys and girls, screen right now. Agree? You shouldn't even be copying anything. So you can put down anything that you have. Okay, put down your phone, your calculator. You don't need it. Okay, so now everything's made of matter. Matter is made of atoms, and atom looks like this. Okay, cool. Okay, you agree, right? Okay. Now, Okay, so have you ever imagined then, in this case, that means the surface of anything, your hand, the computer, your cell phone, the pencil, what is on the surface of anything? Okay, so think about it. What is surfaces? Like surface, like a table, your hand. What is the surface? Your face. What is it? What is it? Think about it. Now, the surface of anything, right? So for example, this is a table. Okay, so now we're going back to the example. And let's say right now, what I want you to do is put your hand on the table. Okay, put your hand on the table. Right, this is the hand because I say so. My drawings are really bad, but that's a hand. You feel a surface, right? You feel like you're touching something, right? Okay, but what is really that you're touching? Now we're gonna look at this world with a very powerful microscope. Okay, this is my magnifying glass. Okay, it's atoms, right? We are made of atoms. The tables are made of atoms. So technically speaking, the whole world is made of, it is. The whole world and everything in it is made of atoms. So what does it really look like if you look at this surface that you're touching right now? Okay, so here we go. Now, here is your hand. Your hand is a whole bunch of nucleus, right? A whole bunch of nucleus, which is positively charged. And then a whole bunch of electrons that are negatively charged floating around on the outside, right? So a whole bunch of electrons. Electrons are always outside because it's orbiting the nucleus, right? So electrons are always outside like this. Okay, so this is your hand. Yes, there are many, many more layers of these positive and negative charge, but the layer that's on the outside will look something like this. This is your hand, ladies and gentlemen. Now, here I'm going to draw the table. The table is made of a different types of atom, so it has a different type of nucleus. That's true. Maybe more carbon or less, and then it's just going to be like layers after layers of those nucleus. And then what? And then electrons, right? And then you have a sea of electrons that are, just orbiting around like this. So I'm just going to randomly put electrons, like electrons. Okay, so this is table. Ladies and gentlemen, I'm about to make you very sad. Okay, are you ready? Everyone, are you ready? Okay, so now I'm going to put your hand on the table. Watch. Your hand will now be on the table. So when your hand is getting really close to the table, what happens to the space between the electrons on the table and the electrons on your hand? It decreases, right? Now, can you answer this question for me? When an electron get too close to another electron, what happens? They're both negatively charged, right? So when you bring one electron too close to another electron, what happens? What happens to an electron when it's too close to another electron? They repel. Yeah, in chemistry, but they still, right? In chemistry, we say atoms will share electron. Well, that's only true because you have the, for example, the nucleus is positive, so they want to share more electron. But if you just take two electrons on its own, then you put them really close to each other, they repel each other, right? Because negative charge or any type of charge that are the same will repel each other. So electron and electron repels each other. Okay, electron and electron repel. So when you put your hand on the table, the reason why there is a force going up from the table is because of what? It's because the electron of the table is repelling the electron on your hand. And this is actually an electric force, which is one of the four fundamental forces that we talked about at the beginning. Now, but here is the part that will make you really sad then. Wait, so the force between the two electrons gets stronger and stronger, repelling force, when you get closer and closer, right? Now, do you think you can ever get two electrons to actually touch each other? No, you cannot. Okay, put your hand back on the table right now. So does that mean you're not actually touching the table and there's a gap in between? You might not think so. But that's only because you don't have a microscope. There is a gap. You're not touching anything. In fact, touching is an illusion. You are never actually touching anything. The electrons on the skin is always going to repel the electron on anything that you are touching, like the pencil or your computer or your phone. So technically speaking, when you touch your face with your hand right now, there is a gap in between. Or if you accidentally punch someone, you can say, sorry, my electrons on my hand accidentally repel the electron on your face. That's punching. So that makes you extremely lonely, doesn't it? That means from the day that you were born, you have never touched anything. And you will not touch anything for the rest of your life. No one can. Touching is not real. Touching is a sensation. Now, I mean, what you feel is the body, now, because your body is always at 38 degrees Celsius, right? And the surrounding area is always slightly colder, like, for example, the table or the ground. So what you're feeling when you touch something, for example, like the table, what you're feeling, that feeling is actually your body losing heat to that table. Your body is slowly losing heat to that table. So the sensation of the table being touched is a sensation of your body losing energy. Now, if you touch something really hot, then obviously the energy flows backward, right? For example, if you're holding a cup of hot tea, then the energy flows backward. It flows from the hot tea back to your hand. So that's why your hand will get warmer later on. But if you touch a table, your hand actually gets colder after a while, right? Because the table has lower energy, lower temperature. So your body, which is always warm, will lose energy to the table. But you have never actually touched anything. There's always a gap, and that gap will never disappear. Some people ask, really good question though, what about using a knife to cut open something? Are we touching that surface using a knife? No, you're not. You know what a knife is made of, right? What was a knife made of? Usually metals, yeah? Which is made of atoms, right? So what is a knife? A knife is just a very sharp, very thin piece of atoms. This is a knife. Maybe at the edge. Okay. So that is normal force. Now we will stop first for a moment. There you go. Now, so that's basically what I want to talk about today. The last bit of this should be something that usually this is something that you usually don't learn in high school yet, right? About the nature of normal force. But now you know what normal forces are. Normal force is a force from the surface that you are touching repelling you because there are electrons on the surface and there are electrons on the things that are touching it. And since everything are made of atom, everything have those electrons. So that means tonight when you go home and you hug your brothers, sisters, you give them a kiss, your lips is not really touching their lips. There's always a gap, however small that is. I mean, technically, right? Kissing them, kissing your brother and sisters, goodbye or good night, meaning that the electrons on your lips repels the electron on their lips, right? That's all there is to it. So, okay. So one last thing I've got, which is over here. So if you drop a book from 2 meters right here, so that's the book, you drop it from 2 meters. So now it's no longer touching any surface, which means no more electron repelling normal force. So at this moment, while the book is dropping, from the sky, before it hit the ground, the only force on this object now is truly just force of gravity. Now, and since this force of gravity is now unbalanced by anyone else on the other side, this system now has a net force. And the net force will be, well, whatever that force of gravity is, mg, right? So what would the book do if the forces are unbalanced? Now, Newton's first law says when the forces are balanced, when the net force is 0, an object will stay at rest or it will go at constant speed, which is stay in motion, right? But if the forces are unbalanced, you will not be at rest then, and you will not be at constant speed. Now, what is the opposite of constant speed? Well, acceleration. And that is why in the last chapter, when we did our free-fall calculation, we say an object falling from the sky is always going to be affected by Earth's gravity and is always going to accelerate downward with the speed or with the acceleration on Earth, 9.8 meters per second. So an object with an unbalanced force will always accelerate somewhere. Okay? An object with a balanced force will not accelerate, either constant speed or stay at rest. Okay? So that's the difference. Now, Lick's class, so Newton's second law, is going to deal with this exclusively, which is what about unbalanced forces? So today, that ends our discussion. All the forces balance out, and an object at rest should stay at rest, an object in motion should stay in motion if there are no net force. All right, that's it. Goodbye.